Say you have some rotational vibrational spectrum of a diatomic molecule like carbon monoxide. It will likely look something like this, where what you have is a P branch with energy levels that are getting farther and farther away, and these show you rotational lines next to a vibrational fundamental, and then an R branch off to the right where the lines are getting closer and closer together rather than farther away. And both of these things together can tell you something about the bond lengths of the diatomic molecule in the ground vibrational state and in the first excited vibrational state. But how do you get that information out of the spectrum? That's what we're going to figure out in this video. The equations for the rotational levels surrounding the fundamental vibrational transition are given up here. So the P branch looks like this thing, and it has, notice it centers around the fundamental frequency, and it depends on BE tilde and alpha E tilde, and then the equation for the R branch is over here, right? And they look really similar, but they're not exactly the same thing. And the basic idea is that we're going to try to fit our measured data to these equations so that we can use the measured data to get estimates for what these parameters, these theoretical parameters, ought to be. It's a little annoying though because these are two separate equations. It's not just one equation. So what we've got to do is first combine the two by writing them into the same equation, and we can do that by defining a new variable called J bar. So we're going to set J bar to be equal to minus J when we're inside of the P branch. And we're going to make it equal to J plus 1 when we're in the R branch. And so if we rewrite these two equations using J bar now, you'll see that both of them fit nicely into this same equation here that I'm calling E all, where we have, when J bar is negative here, it looks like P branch, and when J bar is J plus 1, it looks like R branch. Okay, so this will let us write all of the data into one single equation. And so the next steps is that we're basically going to plot this data now. So we're going to take all of our observed data. We're going to plot E observed against J bar. When you do this, it'll look a lot like a straight line, but there is an underlying polynomial, so quadratic equation underneath it. And then we will fit a line to this data, and we can extract out the equation of the best fit line. That's going to look something like y equals ax squared plus bx plus c. And now just by comparing the two of these, you'll see that if x is J bar, then this coefficient A will be minus alpha E, the coefficient B will be 2B plus alpha, and then the coefficient C will just be the fundamental transition energy. Okay, so next let's see how we can actually do this, and we're going to do this using Google Sheets. Okay, so I'm going to use some synthetic data here just to demonstrate what we're doing. I'm trying to organize this a little bit, so I'm keeping the P branch data here. I'm going to label P branch. Remember, P branch goes from 1, 2, 3, and so on. And then the R branch starts at 0, goes up 1, 2, 3, and so on. So we take these values, and we can use these directly to figure out J bar, which is just minus in the P branch, and then you do plus 1 from R to get to the J bar. So we have our x-axis values here, and then we have our observed energy values here. And so let's go ahead and just make a plot out of this. So we can select both of the columns and then go to Insert, Chart. So it does some really dumb and goofy defaults. So we're going to have to undo some of that. So you do that by going to Add an x-axis. So the x-axis we want to be J bar. So we're going to add that there. And then we want to remove this J bar series from the actual thing it's plotting. And so now we have something that makes some sense, right? It goes from minus 3 to 3 or so. Let me shrink this a little and make it more visible. And it looks kind of like a straight line at this level of being zoomed in, but That's just because we're looking at a really small piece of it, and if you looked at a larger piece, it would look more like a parabola. And you can see the plotted values here are at -3, -2, -1, and so on. Okay, so next thing we do is make a trend line for this. So we go to Customize, we pick Series, and then add a trend line by clicking this box down here. And then this adds a trend line, but we want a polynomial one because we want to fit it to something that has x squared. We want a second degree polynomial, so the default is fine. And then the last thing is we want to be able to see the equation, and so we will add a label and have the label be use equation. And so this will write out the equation straight for us right off the bat. Okay, and so basically from this, we can directly read off all of the values in the fit that we want to look at. So let's just write down each of these coefficients. So we're thinking about this in terms of if the quadratic equation was written as ax squared plus bx plus c, then we would have a is -0.0122, b is 3.91, and c is 2185. Great, so now we can use these and we can use them to figure out what alpha E would be, and then what BE would be, and then what omega E would be, or omega 0 to 1 would be, right? So this is the 0 to 1 transition. Okay, so first off, alpha E is just the negative of this slope, so it's minus this beast. We're not going to accept that autocomplete. And then remember, the x coefficient is 2 times BE minus alpha E. And so if we want to get back BE, what we're going to do is 0.5 times, this is equal to 0.5 times the B coefficient, and then we're going to add on alpha E. Great. And then this is just equal to the C coefficient. 2 times. Great, and so now we have alpha E, we have BE, and we have omega 0 to 1. So this will tell us directly the energy of the vibrational transition between 0 and 1, and then the parameters of the rotational constant that tell us how the rotational constant changes as we look at higher and higher vibrational states.